Hello and welcome to this video on complex number problems. So uh, get started. We go to slides, algebra, complex numbers. Now we are into 26th set of problems. So as always, we will solve 10 problems in this set. Without further ado, let's get started. Let's put this in full screen mode. So as always, I will repeat that when I am stating the problem, try to solve the problem yourself. Only if you cannot solve the problem yourself, then look at the solution. So question 251 says that if alpha, beta, gamma, delta be the real roots of the equation x to the power 4 plus bx cube plus cx square plus dx plus c is equal to 0, show that a square into 1 plus alpha square into 1 plus beta square into 1 plus gamma square into 1 plus delta square is equal to a minus c plus e whole square plus b minus d whole square. So from polynomials, we know that if alpha, beta, gamma, delta are the roots of the given equation, then a into x minus alpha into x minus beta into x minus gamma into x minus delta is equal to x to the power 4 plus bx cube plus x square plus dx plus c. Now we substitute x is equal to I. We get our left hand side as a into I minus alpha into I minus beta into I minus gamma into I minus delta is equal to ai to the power 4, that is a, plus bi cube, that is minus bi, plus ci square minus c plus di plus c. So equivalently, this is equal to, so 1 plus I alpha plus 1 plus I beta plus into 1 plus I alpha into 1 plus I beta into 1 plus I gamma into 1 plus I delta, and a should be here, a is missing, is equal to a minus ib minus c plus id plus e. So what we have done is we have divided from I to the power 4 on left hand side. I to the power 4 is 1, so it doesn't make a difference. That's how we have got 1 plus I alpha and so on. Once we have this, we take the modulus and square and we get the desired result. Question 252 says that if ai belongs to the set of real numbers where I is equal to 1 to n, and alpha 1, alpha 2, alpha n are the roots of the equation, then x to the power n plus a1, x to the power n minus 1 plus a2, x to the power n minus 2 and so on up to an minus 1x plus an is equal to 0, show that product from I is equal to 1 to n of 1 plus alpha I square is equal to 1 minus a2 plus a4 minus so on whole square plus a1 minus a3 and so on whole square. So this problem is similar to the previous problem, just that it is a generalization of that case. Earlier we have 4 roots, now we have n roots. So similarly we proceed by writing x minus alpha 1 into x minus alpha 2 up to x minus alpha n. We have x to the power n plus a1 x to the power n minus 1 and so on, that is the equation, is equal to 0. Substitute x is equal to I, we get I minus alpha 1 into I minus alpha 2 up into I minus alpha n, and we have I to the power n and so on up to right hand side. And then you take modulus n square and you will have the desired result. Question 253 says that if the complex number z1, z2, z3 are the vertices of an equilateral triangle such that mod z1 is equal to mod z2 is equal to mod z3, prove that z1 plus z2 plus z3 is equal to 0. So since z1 mod z1s are equal, which is equal to r, therefore origin will be the circumcenter of the triangle. Now since the triangle is equilateral, the circumcenter and origin will coincide. Therefore origin is also centroid. Okay, it should be that circumcenter and centroid coincide. Okay, therefore origin is also centroid. Thus we can write that centroid is z1 plus z2 plus z3 by 3 is equal to 0, and that's why z1 plus z2 plus z3 is equal to 0. Question 254 says that if z1 plus z2 plus z3 is equal to 0 and mod z1 is equal to mod z2 is equal to mod z3 is equal to 1, then prove that the complex number z1, z2, z3 are the vertices of an equilateral triangle inscribed in a unit circle. So we have just proven that if z1 plus z2 plus z3 is equal to 0, then that means centroid of the triangle is the origin. Circumcenter is also origin as Zi lies on the circle mod Z is equal to 1. Since circumcenter is same as centroid, making the triangle equilateral, and we have a circumcircle with unit radius. Question 255 says that if Z1, Z2, Z3 be the vertices of an equilateral triangle whose circumcenter is Z0, then prove that Z1 square plus Z2 square plus Z3 square is equal to 3Z0 square. So since the triangle is equilateral, therefore circumcenter and centroid will be same. Since Z0 is equal to Z1 plus Z2 plus Z3 by 3. Also for equilateral triangle, Z1 square plus Z2 square plus Z3 square is equal to Z1 Z2 plus Z2 Z3 plus Z3 Z1. Okay? So how do we have this result? This result comes from the fact that since the triangle is equilateral, mod Z1 minus Z2 square is equal to mod Z2 minus Z3 square is equal to mod Z3 minus Z1 square. From there we have this result. Alright. So once we have that, we can write on the left hand side, we write this as 3Z0 square. So we can write that 3Z0 is this, we square it, we get Z1 square plus Z2 square plus Z3 square into 2 Z1 Z2 plus Z2 Z3 plus Z3 Z2. Now what we do is that this equation, if we compare with this guy, this equation, then we will have Z1 square plus Z2 square plus Z3 square is equal to 3Z0, because 2Z1 Z2 Z2 Z3 plus Z3 Z2 will be equal to Z1 square plus Z2 square plus Z3 square, which we have substituted here. Question 256 says that prove that the complex number Z1 and Z2 and the origin form an equilateral triangle if Z1 square plus Z2 square minus Z1 Z2 is equal to 0. So from the same relationship where we have written that Z1 square plus Z2 square plus Z3 square is equal to Z1 Z2 plus Z2 Z3 plus Z3 Z1 for an equilateral triangle, in this case Z3 being 0, we just substitute Z3 is equal to 0 and we have the desired result. Question 257 says that if Z1 and Z2 be the roots of the equation Z square plus AZ plus B is equal to 0, then prove that the origin Z1 and Z2 form an equilateral triangle if A square is equal to 3B. So from the previous problem, we have Z1 square plus Z2 square minus Z1 Z2. So this we can write as Z1 plus Z2 whole square is equal to 3Z1 Z2. Now from quadratic equation, we know that sum of roots is minus B by A, where B is the coefficient of X and A is the coefficient of X square. In this case, minus B by A will be A, because the coefficient of X is A and the coefficient of X Z square is 1. So minus A by 1 will be minus A and square of that will be A square. And Z1 Z2 will be B. So 3Z1 Z2 will be 3B. Question 258 says that let Z1 and Z2 and Z3 be the roots of the equation Z cube plus 3 alpha Z square plus 3 beta Z plus gamma is equal to 0, where alpha, beta and gamma are complex numbers and that these represent the vertices A, B and C of a triangle. Find the centroid of triangle ABC. Show that the triangle will be equilateral if alpha square is equal to beta. Since alpha, beta, gamma are given here in the form of this equation, that is Z cube plus 3 alpha Z square plus 3 beta Z plus gamma, we can write that Z1 plus Z2 plus Z3 is equal to minus 3 gamma, where Z1, Z2, Z3 are roots. Z1, Z2 plus Z2, Z3 plus Z3, Z1 will be 3 beta and Z1, Z2, Z3 is equal to minus gamma. The centroid will be given by Z1 plus Z2 plus Z3 by 3 is equal to minus alpha. Now, okay, yeah, yep, this will be minus alpha because Z1 plus Z2 plus Z3 is equal to minus 3 alpha. So by 3 is minus alpha. Now triangle will be equilateral if Z1 square plus Z2 square plus Z3 square is equal to Z1 Z2 plus Z2 Z3 plus Z3 Z1. So we can say that Z1 plus Z2 plus Z3 whole square is equal to 3 into Z1 Z2 plus Z2 Z3 plus Z3 Z1. Now this is nothing but 9 alpha square. This is nothing but 9 beta. So 9 will get cancelled and alpha square is equal to beta. Question 259 says that if Z1, Z2, Z3 are in AP, prove that they are collinear. This is a very easy problem. We are given that 2Z2 is equal to Z1 plus Z3. This is of the form of section formula where Z2 is the midpoint of Z1 plus Z2. So we clearly see that it divides Z2, Z1, Z2 divides Z1, Z3 in equal parts. So the complex number must be collinear. Question 260 says that if Z1, Z2 and Z3 are collinear points in Argand plane, then show that one of the following holds. Minus Z1 into mod Z2 minus Z3 plus Z2 into mod Z3 minus Z1 plus Z3 into mod Z1 minus Z2 is equal to 0. Or Z1 into mod Z2 minus Z3 minus Z2 mod Z3 minus Z1 plus Z3 mod Z1 minus Z2. Or Z1 into mod Z2 minus Z3 plus Z2 mod Z3 minus Z1 minus Z3 mod Z1 minus Z2 is equal to 0. So since the points are collinear, either Z2 will divide Z1 Z3 internally or externally, or Z3 will divide Z1 Z2 internally or externally. That means the points are definitely collinear. Case is whether Z2 divides this externally internally, or Z3 divides Z1 Z2 externally internally. So we use the condition for collinearity using the determinant with the rows Z1 Z2 Z3, Z1 bar Z2 bar Z3 bar is equal to 0, 1 1 1. Sorry, Z1 bar Z2 bar Z3 bar 1 1 1 is equal to 0. Now it's a straightforward evaluation of this determinant to get the desired condition. Again, we have not yet covered determinant, so you might want to skip this problem. So with this, we come to the end of 26th set of problem. If you have found this video useful and informative, please subscribe to the channel, like the video and share and comment so that this video reaches many more students like you and I get some motivation to make more such video. Thanks a lot for watching. Have a nice day.